All right, so we've got our overall equation, delta G equals delta H minus T delta S. And remember, we said that this needs to be negative for this reaction to occur. And so if we think about what does the value of delta H need to be to kind of promote this, well, if we wanted delta G to be negative, we also want delta H to be negative, right? So if delta H is negative, it favors the reaction occurring. And remember, a negative delta H will be an exothermic reaction, right? So again, delta H is the enthalpy of the reaction. And in terms of chemistry, it's essentially just the heat of the reaction, because delta H is equal to Q at constant pressure, which most chemical reactions are. And it's essentially a representation of the change in kinetic energy. One big thing in chemistry and one big misconception is bond formation. So for example, if we've got a fluorine and a fluorine here, and we've got energy over here, right? They've got their two atomic orbitals, and then they're going to combine to form some molecular orbitals. You can see when they form a bond right here, individually, they're higher in energy, and then when they form a bond, they go lower in energy. And so forming a bond is an exothermic process. And to look at the overall delta H of a reaction, we can take a look at how much energy it takes to break bonds versus how much energy we get back out to form these bonds. And so we can look up what's known as bond dissociation energies. And you did this back in Chem 101, right? These bond dissociation energy is the energy required to break a bond, right? And so you can look these up in tables. And these tables will give you them in their standard state, right? So this little degree symbol here, if you think back to Chem 101 and 102, means at standard conditions. 1 atmosphere of pressure in their normal state, and usually room temperature. And so we can take a look at an example of this, right? So if we have methane, CH4 plus Br2 to form a CBr bond, bromomethane, and HBr, right? We can take a look at these bond dissociation energies. And so we should think about what bonds are being broken and what bonds are being formed. So if we take a look over here, on this left, we've got this CH bond, and we're going to break this. We've got this Br-Br bond. We're going to break this. And then over on this other side, we're going to form this CBr bond, as well as this HBr bond. And so you can look up these values in a table, right? So you can look up CH, CBr, Br, Br, and then HBr. And if you find them, you'll find, delta H at the standard states in values of kilojoules per mole. This will be 435, 293, 193, and 368. And so you just identify them, right? So here's 435. And remember, we're breaking this bond, right? So we're going to take 435 kilojoules of energy we have to put into the system to break this bond. Same thing with this Br-Br bond, right? We're going to put energy into the system to break this bond. And then we're going to form a CBr bond. If we're forming this bond, that means we're getting energy out. So we're going to get negative 293 kilojoules per mole. And then finally, this will also be a negative. And then we just sum all of these values to get negative 33 kilojoules per mole. meaning that this is exothermic, right? So you can look at almost any reaction, see which bonds break, which bonds form, take a look at some bond dissociation energy tables and tell whether this is going to be an exo or an endothermic reaction. And of course, you can draw a reaction diagram coordinates, right? So we can have delta or H here, enthalpy on this y-axis, and then reaction here. And then we go from reactants. In this case, it's negative, so products, right? This gap right here is your delta H, right? So in this case, this is exothermic. And so it gives off heat. Notice that these are just state functions, so they just tell you the beginning and the end. They don't tell you how you got there, right? Maybe you went over this big hump, or maybe you went over this little hump, right? You don't know that from the delta H. You just know the end states. And of course, for endothermic, right, this is the reactants right here. The products would be higher in energy. So just some basics about enthalpy. We won't really spend too much time or effort on it.